Hello everyone, this is Space Cafe Podcast and I am Marcus. I really like the feeling when something blows me away, blows my mind. Ideally, something unexpected that, because I suddenly see it from a new angle, pulls the rug out from under me. Like the following episode. I had the great pleasure to be in Geneva on September 10, 2008, when the first proton beam was shot through the LHC, a 27-kilometer tunnel at CERN, the world's largest particle research center. The fact that the tunnel has to be cooled to minus 271 degrees Celsius and that the protons travel at close to the speed of light would be mind-boggling enough. But now it comes. I asked one of the physicists with which precision they work, how I can picture that. The answer was a devastating analogy. So, take two pins, bring them 27 kilometers apart and shoot them at each other so that they meet with their tips. Period. End of message. Mind blown. Today, people at CERN are already thinking about a 100-kilometer accelerator. My mind is not granted any rest, it seems. My guest today is in no way inferior to such dimensions. Ian Carnelli.
My pleasure.
Is an astrophysicist and, in his current role, director of the Hera mission, a joint mission between ESA and NASA to deflect the asteroid Didymos. Planetary Defense Mission is the official name of the undertaking. I think it goes without saying that we cannot miss this treat, right? Let's get right into the fun. ESA and NASA are undertaking a spectacular mission to repel an asteroid. Are we in danger?
Haha, that's a good question, Marcus. No, I mean, there's no real danger today or identified asteroid that is coming towards us. So we should all take a deep breath and relax. For the moment, there's no hazard pointing towards us. The issue is, though, that there are so many objects out there, and statistically, one day it will happen. So if we look at the Earth, there are multiple asteroid impacts, and there are scars on our planets. And if you look at the moon, it's every night you see those craters. Now, fortunately, we have an atmosphere protecting us, but it doesn't always work, or it's not enough. So we need to be prepared, and we've been working for that for God knows, 20 years, to make sure that, we know what we can do. The nice thing about it is that we can actually, it's a natural hazard we can actually prevent, differently from earthquakes or any other hazards. I mean, the asteroid impact, today we have the technology, or we think we have the technology to prevent it.
And now this is something to put it to the test, so to say.
Exactly. So it's like a life insurance, you want to be sure that our technology is ready, that it's tested and actually works as we think it will work. And for that, we need a real scale test.
Has something like this been tried before on a smaller scale?
Well, there has been for many years, we've done tests in laboratories for like shooting small projectiles with what we call gas guns. So there are guns who shoot at kilometer per second, small projectiles on pieces of rock or concrete, different type of materials. And scientists have been studying, the results of those impacts. But the energy scales in the laboratories are not comparable to what we actually need. Besides the fact that there's gravity and therefore, stuff floating around, you don't really know, how it's going to behave.
Interact.
But we really need to have, so we have used those experiments, to start building our models, our impact models, and they work to some extent. But the level of energy that is involved in a full real asteroid deflection goes beyond anything we can do on Earth. Therefore, like with every experiment, there's so many unknowns that we need a test actually to be able to pin those down.
So what are the odds that an asteroid impact the size of the famous or the infamous dinosaur extinction event could happen in the future?
So those type of events are thought to happen every few thousands of years, so several centuries. And today we have a network of telescopes looking at the sky every day and building our catalogs, so understanding how many objects, where they are, how they're moving. And we think we know a little bit more than 90% of the big asteroids. So the famous dinosaur killers, the ones that are, just to put it in easy terms, above 1 kilometer diameter. Those are the ones that could have a catastrophic, like a planetary effect. And so we're quite confident that none of those will impact the Earth in the coming centuries. The real issue today is with the small asteroids. The way we detect asteroids is by detecting the light that they reflect, the sunlight that they reflect. So the smaller the asteroid, the darker the asteroid, the more difficult it is to observe it. So, and when you think of a 100-meter diameter asteroid or smaller, you can imagine how difficult it is to detect it from Earth. And there are many more of those asteroids than the big kilometer size, because actually asteroids typically have gone through fragmentation processes. So they've collided, maybe one or twice. So they've broken up in several pieces. So there are many more of the small asteroids than the bigger ones. And the energy of a small asteroid of a 50 or 100 meter size can still destroy a region like Ile-de-France, like the Berlin area, and would generate millions of casualties should impact on an area like that. So it's not something we can ignore. And therefore, today, what we consider to be the highest probability threat is coming from those small asteroids. And that's why we're targeting Dimorphos, which is an asteroid of about 160 meters in diameter, because it's representative of this class of asteroids.
How far is the asteroid away from us?
So this asteroid is orbiting, like every object in the solar system. And its orbit comes very close to the Earth. Actually, there will be a very close encounter next year in October. And it will be coming at a few million kilometers from Earth. So a few times the distance between the Earth and the Moon. And then it goes all the way slightly farther than Mars and coming back. So the distance basically goes between a little bit more than Mars and the Earth. And DART is going to impact it when it's actually very close to the Earth, because we want to observe it with ground-based telescopes and radars so that we can benefit from the distance to gather data.
Fascinating. Before we go into details of the actual mission, a couple of years ago, we had a pretty interesting visitor from wherever it came from. I'm talking about Oumuamua.
Yeah.
Was that an object that you were also interested in, or is it an anomaly when it comes to asteroids? Because no one really knew where it came from, what it is, maybe a spaceship, an alien spaceship or whatnot.
Absolutely, yeah.
So in how far does that fit into your world?
That was an incredible encounter, wasn't it? I mean, honestly, we were all blown away with the discovery, thinking that an object from another solar system can basically come to us. Honestly, it just opens so many questions and so much thinking. In terms of planetary defense, I must say that we are not overly concerned because after all, the solar system is such a huge place. Think that there are planets in our solar system that in our lifetime will never orbit full-time the sun. I mean, they are so far away. It takes decades and decades of traveling at 20, 30 kilometers per second to reach them, that an object the size of a few hundred meters or a kilometer, I mean, we would really need to be super unlucky to be hit by something like that. Statistically, it's almost impossible. Now, almost, and statistics means that there is a small chance to be impacted by such an object. Frankly speaking, I don't think there's anything you can really do about it because it's such a low probability in such a big place that it's basic, and they travel at such a high speed that it's virtually impossible to intercept any of those objects. As a matter of fact, I was reading some articles stating that it looks like statistically there are probably a few objects like that like 4 or 5, if I remember the paper, that are crossing our solar system every year. So the chance to see it is actually, and to discover those is extremely small. And I think we were very lucky to find one.
Very interesting. So before we talk about science and your mission, please excuse a very blunt and maybe stupid question. But if push came to shove and an object appeared on our radars with 100% impact probability with Earth, is there anything, anything we could do? Would we, put a couple of nukes on some of Elon's rockets and fly towards that object? Would that make sense? Or would we be completely hopeless and defenseless at the moment?
You mean for an interstellar object?
Yes.
If we were, well, we would have very little time. But I think, because they're traveling at 60, 70, 80 kilometers per second. I think if we had enough time, yes, we would probably try to do something like that.
Okay.
In the worst case, yes, you would try to do something like that. Chances that it works, honestly, I shouldn't say it, but the main issue with a nuclear device is that typically you would want to try not to fragment the object, because otherwise you create more projectiles and maybe the thing is even worse.
You're raising the odds of destruction.
Yeah, but you would want to set it off at a certain distance from the surface, so that the thermal energy would actually sublimate,
pushes the object away,
and create like a jet from the sublimation that pushes the objects away. But okay, of course, if it comes down to an interstellar object, I think anything we would try to do.
It's better to do something than just watch the destruction, right?
Absolutely.
Nice. So let's talk about Hera and the mission. Where does the name come from?
Oh, interesting. It's a very good question. So, how much time do you have? Anyway,
give it a try.
Hera is the result of almost 2 decades of work at ESA. It went through several phases, several mission concepts before we actually came with the Hera one. And the previous one, the previous version was called AIM, was called Asteroid Impact Mission. It would have launched shortly before DART and be there already in time for Didymos, in time for the DART impact. That was in 2015, and in 16, that's when we asked our our countries, our what we call member states at ESA to fund the mission. Unfortunately, in 2016, there wasn't enough momentum to get the funding for the mission. So we went through a period of reinventing, re-scoping, changing payloads, and eventually we came with a new mission, or at least a new satellite concept. And therefore, at the time, there was some confusion, what is now on the mission? What kind of payload? What kind of instruments? What is it going to do? So we also figured that we had to change name to the mission. Otherwise, it was too confusing. So one of those nights, with a few drinks around the table and a few friends, scientists.
That's how a good story starts.
We were talking about, mission names. And I had only one constraint from basically one of my bosses, which is enough with acronyms. We don't want acronyms anymore. We want a name which is self-standing. And in the end, it was one of the scientists who proposed Hera, saying, okay, we still love these asteroids. We love asteroids. And, we definitely, from our simulations, we're quite confident that Dimorphos will still orbit around Didymos after being impacted by DART. So why don't we call it after the goddess of marriage? And, in the sense that Dimorphos and Didymos will stay together also after having a hard time. So that's how we came up with Hera.
Nice. But now you are trying to separate the two, right? How do you feel about separating this?
Well, we're just separating them probably by a few millimeters, to be honest, because the push that DART will give will only change very, very slightly its orbit around Didymos. It's only the push. It's really 0.5 millimeter per second change in velocity. Very difficult to measure.
But over a great distance, it makes a huge difference.
Well, let's say that we will measure it as astronomers today measure the presence or infer the presence of exoplanets, meaning that every time the Dimorphos orbits around Didymos and you watch the light that is reflected, you see a little change in the intensity of the light. And so basically, if you were to, I'm a bit exaggerating, but if you were to watch Didymos through a telescope, you would see the light pulsating a bit. So if you see if you measure the pulsations before and after the impact, that's how you can calculate from Earth the change in velocity. Now telescopes have very good detectors, so they can detect the change. But the effect is actually very, very small.
So what's the spacecraft like? Is it ready for launch? What does it look like? Where is it?
Okay, so actually, the DART spacecraft is really getting ready for launch.
That's the NASA.
That's the NASA one. That's the NASA one that is going to be launched later this year. So they're doing their final TVAC, what we call thermal vacuum tests. So you put the spacecraft in a big chamber, you suck up all the air, you cool down the walls down to minus 200 degrees. You turn on some really impressive lights that create a heat of
radiation
plus 150 degrees. And then you basically bake the satellite as it's going to be baked in space environment, and you check that everything is healthy before you launch it.
How big is DART? Is
DART
that comparable to a small car?
It's a small car, yeah. It's about a couple of washing machines, or a bit bigger, a couple of
and
machines.
And it looks like a satellite.
Yes, it definitely looks like a satellite, not a missile. So it's a rectangular.
With its solar panels.
Yes, absolutely. So it's a long, elongated rectangle, or prism, and has very interesting solar arrays. Differently from others that you might see on regular satellites, actually has this rollout solar array. So it's like two tubes They will roll out and extend the flexible solar arrays. And then as on the smaller sides has on one side there's the camera, which is the main instrument, is a very powerful navigation camera. And the opposite side, there's electric propulsion system, which is looks like a big cylinder, and it's going to it's a technology demonstration. So it's going to demonstrate a powerful thruster that is going to be used in the future for lunar missions.
Wow, fascinating.
So,
can you tell us a little bit about that thruster? So you said it's electric. So so it's like what we're doing on Earth with electric vehicles is also going on in space. So it's all sustainable.
Well, let's say that it's more efficient, a lot more efficient than, let's say what we would, for analogy, call gasoline on our normal spacecraft. So electric propulsion is actually a technology, is not so new. I mean, it's been used already since, almost 2 decades. Early 2000s, I think, was the Deep Space One mission at NASA that flew the first operational engine. Anyway, you're actually using, instead of using the regular chemical propulsion, you're using xenon. And what you're doing is, it's actually liquid. And then you of course, when you open the valve, it's going to become a gas. And then you make it flow through a cathode and an ion. And you create this very powerful electromagnetic field. Before you do that, you ionize the gas. So you basically have all the ions going through this electric field, and they're going to be ejected at very high velocity. So you get a reaction on the opposite side. The advantage is that the ejection speed is extremely high, and therefore the engine is extremely efficient. The disadvantage is that the thrust you get is very, very low, which means that it's an engine that allows you to get eventually very high velocities, and therefore be very efficient. You need a lot of time. You need a lot of time. You need to basically keep thrusting for many years to reach those velocities.
It's like comparable to solar sails.
Exactly. It's what we call low thrust propulsion system, comparable to solar sails. So it's actually an enabling technology when you want to be able to go very far and have a very low spacecraft mass, which ultimately means fitting in a rocket. There's a limit to the amount of mass that a rocket can launch with a certain velocity. So if you need to have to go very far, either you have a very small spacecraft, or you have a spacecraft with such electric propulsion that can complement the energy that is required and cannot be provided by the launcher.
But now the same holds true, of course, for slowing down. That will take the same amount of time, I guess.
Absolutely. So, the advantage with DART is that they don't have to slow down.
because their goal is to crash right into the asteroid, right?
Exactly. So when people ask me why can they have such a short mission? And I say, it's very easy. You get launched, you don't have to brake. You just keep going. And anyway, but typically, low thrust propulsion system, or missions that are based on this technology, they start what we call the rendezvous phase with their target several months before. But it's the only way to reach, for example, some asteroids that are far away and that require very energetic orbits. So go ahead. You can either use electric propulsion, or you need to use other tricks. One of the most common is called flybys, or gravity assists, which means sending your spacecraft close to another planet to slingshot towards your target. That's actually what HARE will do.
So is is DART equipped with some kind of explosives, or is it equipped with super heavy mass, like, I don't know, concrete or whatnot, or gold to produce a nice impact?
No, actually, it's absolutely a straightforward, very common spacecraft. There's no, I mean, there will be
so
some.
It's not especially heavy.
Yeah, no, it's. I think it's about 700 kilos and 800 kilos, and no, there's no additional mass. There's no special material to it. I mean, it's just going to slam into Dimorphos at about 6 kilometers per second, and that's
what's the size? What's the size of Dimorphos again?
160 meters.
160 meters. So you have a small car crash into a 160-meter rock.
Yeah.
I mean, like, it's already fascinating to me that this produces an effect in the first place.
Yeah, absolutely. 0.5 millimeter per second. It's very small. But yes, absolutely.
Nice. So you have the Americans do their thing, what they can do best, take their stuff and hit something, crash into something. Then you have you have ESA, the European Space Agency. And what is your mission?
So our mission is a detective. What we're trying to do is to get to Dimorphos a few years after the impact and study what has happened from close by. So the data that the DART team will gather will be from ground, as I said before, by using telescopes and radars. What we want to do is to go close and personal. So we want to go very close to the asteroid, down to possibly a few hundred meters, a kilometer from the surface.
After impact,
impact. And then.
So there will be no footage from the actual impact because there is no spacecraft to watch it.
Well, actually, there is one. I forgot to mention. DART will piggyback a small CubeSat from the Italian Space Agency called LICIA Cube. These CubeSats are like very small spacecraft, the size of a shoebox. And a little bit like drones. It will be. So
it's your GoPro you're placing in orbit.
Exactly. So they're going to be released or ejected from DART a couple of weeks before the impact and fly along DART. And its purpose is really to take pictures of the impact location, possibly the plume, so all the ejecta that will be released, and also very important, trying to image. Let's say the dark side of Dimorphos, so the opposite side of the impact, so that will allow building a 3D shape model of Dimorphos, and from that trying to estimate the mass of Dimorphos, assuming a certain density. So there will be a small GoPro flying with DART. And taking some pictures, so that is going to be extremely exciting. Honestly, so there will be some image, whereas Hera will come when everything is done. All the ejecta, all the dust environment will be cleaned up. But what we want to do is actually, first of all, take images of the crater. And with very high resolution, so that we can build a 3D shape model of the crater. And this is extremely important. I was mentioning before these ground-based experiments. If you want to validate those codes, those algorithms, what you actually do is to correlate the crater to the projectile. Now, in this experiment, we have all of the data we need. We will have all the data we need because we will know extremely precisely the velocity of DART at impact. We know exactly its shape. We know exactly what it's made of. We know the impact location from LICIA Cube, and we will know the shape of the crater from Hera. And Hera will also collect information about the composition of the moon, we will perform tomography of the asteroid, meaning like an X-ray. We will send very low frequency radio waves that will penetrate, go through Dimorpho, so we'll know exactly the internal structure, so that we will know whether there are voids or it's a monolithic object. We have all of these.
How deep can you look?
We'll go all the way through the asteroid.
Wow.
So we will see everything inside, and we'll take multiple.
Fascinating. So you get
shots.
you can produce a 3D model of the asteroid.
Yes. Well, that's what we'll do.
Fascinating.
And from all of that, all of the data, this will allow something extremely important. Will allow us to validate these numerical impact codes, and that's the fundamental aspect of this double mission. Because with all of these data, then we have the information we need to say, okay, if another asteroid with other properties will come one day, we have the right tools to know how to deflect it, because we can design the right deflection mission.
Fascinating.
So it's very important for us to reach Didymos and gather all of these data.
So what is the time difference between the actual impact and the arrival of Hera?
Is about 4 years.
Okay.
DART will impact in 22, and we will reach Didymos at the end of 26, beginning of 27. Actually, we'll start.
And why so late? Why not earlier?
Well, because that's because we need to break. So it takes us.
Okay.
So unfortunately,
we need a couple of years to break.
Yeah, I mean, it takes. Let's say that we need to match exactly Didymos velocity, or in other words, we need to fly the Hera spacecraft exactly on the same orbit as Didymos, which means going on this very elliptical orbit that will bring us all the way to Mars and back. Whereas DART can just go and and take a shorter route and doesn't have to match such a very elongated orbit. So it takes us some time. It does take us some time to go there. As a matter of fact, we wouldn't have enough energy if it weren't for Mars to be at the right place when we want to go to Didymos and give us this slingshot. So that will make us save quite a few 100 kilograms of propellant.
Fascinating. So, and the actual amount of deflection, that is measured from Earth. That has nothing to do with Hera, right?
Well, that will be measured from Earth quite precisely, but of course Hera will go there and will perform another type of measurement, and we will also measure it from locally, let's say and therefore we can compare results.
Let me I need to reiterate on this observation because it's so mind-blowing. You have an object that's a couple of million kilometers away. Then you deflect it at the amount of 0.5 millimeter or 1 millimeter, and you can observe that from Earth.
Absolutely.
That's crazy. Absolutely crazy.
Yes. That's how precise you can. Well, the amount of precision, of course, depends on how many measurements you take of these light curves. I'm not an astronomer, I'm not expert, but you can imagine that next year, at the time of impact, there will be probably half of all the telescopes on Earth looking at Didymos and gathering data. So there will be a huge campaign to look at this object and gather a lot of data, so they can have a very precise, very precise measurement. I mean, when we fly spacecraft in space, you can actually measure the position of a spacecraft to a few hundred meters, and its velocity to 2 millimeters per second. So that's how precise today's radio tracking systems are for satellites. And you actually need that kind of precision when you want to land on another planet, for example, when you want to do these gravity assists. Actually, Hera will bring a new transponder, so a new radio system and we'll have even more performance radio tracking for our satellite. So I think we'll break another record in spacecraft tracking accuracy with Hera. It's going to be an interesting one.
Fascinating. Let's go back to DART. So I would like to really understand the precision that's going on here. When we talk about DART, it's like shooting a bullet towards our target. So only a very far away target. So is that one shot? Do they have one shot, or are they shooting it in the right direction and DART is self-correcting its course?
Well, I would say that it's more like shooting a missile against another missile. That's how, and you're doing it at millions of kilometers away. So that's how crazy the experiment is. And even crazier than that, DART will not be able to see its target a few hours before impact, because that's how small Dimorphos is compared to Didymos. So you are actually targeting for most of its time Didymos. It only at the last moment you see the little moon orbiting around, and you have to distinguish between the two objects and actually tell the computer that the second object is not noise from the detector or from the sensor. You know, when you take a picture in a very dark environment and you have all of these pixels, this is called noise. So you have to tell the computer that that dot is actually not noise, and that's actually what you're targeting. So that's how crazy this experiment is, how difficult. So APL, I'm absolutely confident that they will nail it. They are fantastic. And yes, they do have only one shot.
They have one shot. Can DART adjust its trajectory during flight?
Yes, they have. As I said, they have the electropropulsion system, and they will have, on top of that, they also have chemical thrusters to correct. They will need those actually to correct the trajectory, and the final targeting is done locally. So it's not done by the rocket that will launch the satellite in space.
Okay. Fascinating.
Yeah.
So you're expecting the results you're expecting should be equal to the theory behind the mission. So the theory predicts this and that deflection. So you're expecting no difference here, or what is the likelihood that something completely different could be happening?
I would personally say that if I have to be honest and see all the space missions, the results we'll get from the mission will be completely different from what we expect.
Like what?
No, I mean, today there is a fundamental parameter, and that's actually what we are all interested in, which is called the beta factor. So when you want to deflect an asteroid, is the push that is given by the impacting spacecraft, so that by the kinetic impactor. But there's also this additional push that is given by, let's say, Mother Nature. When you impact the rock will be ejected from the asteroid. Rocks will be ejected in dust and boulders, lots of stuff. Imagine all the volume of the crater will be ejected. Mm-hmm. And this is like a jet engine. It's going to provide some thrust and provide additional push, which is, according to theories, it can go up to, let's say, tenfold what the impacting spacecraft can do, or maybe sometimes even more. It depends on many things, on the composition of the asteroid, the way you impact it, if you're impacting a boulder or some sand or all kinds of things. If it's a porous rock and you're compressing the voids like an airbag, or if it's a monolithic rock and then maybe the shock wave actually reflects on the front and even detaches material on the opposite side, and therefore actually has a counter effect to your, to your impact. So it's a very complex dynamics. I think all of this will play, and it will take us years to reconstruct exactly everything that has gone through this impact experiment. So I think there will be a lot of surprises, a lot of new theories about how asteroids react to collisions. And that's why many scientists are actually interested not only from the perspective of planetary defense, but from the perspective of the solar system formation. Because, as I said before, the history of the formation of the solar system is a history of collisions and collision and accretion of material. And therefore, having more information about these type of events provides clues about how the solar system has formed, and possibly could also change some of the theories about the formation of the solar system. So I think there will be a lot of excitement and a lot of unknowns and a lot of surprises from these missions.
Say, Ian, is this mission actually, is it a scientific mission only, primarily? Or is this mission proactively being watched by governmental bodies, by the military, because it's also concerning security issues, security matters?
Absolutely. Well, I must say that there was some concern, some concerns years ago about the interest of military. And, there's always this, this debate about military in space. We have never been approached by military, and I've never heard any interest of military about our mission. So my honest answer is that this is a purely, let's say, scientific mission, whose result, however, will be providing very important information to governing bodies. So there will be reports and several meetings at UN COPUOS, so United Nations, and several other governmental bodies that will be informed about the effectiveness, the results. Of course, we're being funded by those governments, so we will provide all the feedback, all the scientific knowledge, and everything. And the cool thing about this is that everything will be completely public. So we have an agreement with the governments that all the results from the instruments, all of the data will be completely public and will be made available to the public as soon as the data is what we say calibrated. So once we correct the data for temperatures, for all the various elements, they will be made available to the public.
Speaking of data and sensors and instruments, so is this mission also a mission that brings along instruments and sensors that are not particularly part of that mission, but they are just taking advantage of a spacecraft going in that direction to piggyback sort of on a mission and do something completely different?
Let's say we have a lot of instruments on air. I should say first. So just to recap, we have optical imagers like normal cameras. We have thermal cameras to look at the temperature. We have hyperspectral cameras looking at different wavelengths to understand the material composition. I mentioned already the low-frequency radar. And these two CubeSats, we also bring with us two CubeSats with accelerometers to understand what is the let's say the gravity field of the asteroids, but also the elasticity of the surface when they will land on the surface, and see how they bounce. Now, let's say all of these instruments are, of course, have a very strong relation with the information we need for planetary defense, but at the same time, they also have other interests, their own interest about asteroid science. Other things we're looking at, and this is going towards actually your question, is what else can we do with these instruments? And there are a couple of things that we're looking at. One is using, for example, the radios on board the two CubeSats to measure the distance between the two CubeSats or Hera and the CubeSats in a very precise manner. As I said before, radio waves and radios have the advantage that you can measure distances and relative velocities very, very accurately. So we're actually going to use one of the CubeSats as a probe for the gravity field of the asteroids. So we were going to let it free float and see, and then monitor it through the radio and see how fast it's being attracted by the two asteroids. And by that, we actually measure the gravity field of the asteroids.
So there's enough mass to the asteroids to produce gravitational pull.
Yes, it's lower than the pull you have holding a A4 paper sheet on your hand. It's much less than that, but wow. there is some. And actually the environment is absolutely crazy. It's what we call a low gravity environment. I think it's close to no gravity environment, but, let's say that there are two main forces acting, in that environment. One is the gravity of Didymos and Dimorphos. So actually two gravity systems that are changing. And then there's the pressure of the sun on the spacecraft, and the two can become very comparable in terms of forces. So actually, the two CubeSats will use those forces in a very intelligent way. They will fly what we call photogravitational orbit, which is putting themselves in an orbit where the sun and the gravity have an equilibrium, and therefore the orbit of the spacecraft becomes stable. And then you don't need to control the orbit, or you can avoid controlling the orbit.
It's like a Lagrange point.
It's kind of a Lagrange point. Similar. The concept is very similar, exactly. But you're actually using the sun and the gravity field of the asteroid. So, we're going to use the instruments to look at the gravity. We're also using, for example, we'll also play with a laser on board Hera. We have a laser altimeter. We'll probably shoot the laser to the two CubeSats, also to measure the distance. And we're also looking at, for example, taking images of the asteroids, and compare, the motion of the asteroids against the background stars, to see if we have any strange dynamics in the asteroids. So those are type of experiments we will do, which are, let's say, beyond the baseline, goals of each instrument.
What will happen to Hera after its heroic mission?
So the current baseline is to actually land Hera on one of the poles of Didymos.
Like so, land or hard impact?
No, it's probably going to be a soft landing. The issue is that, of course, Hera is not designed to land. So eventually, Hera will actually die because the temperature of the surface is extremely high, or we'll probably turn it off before it soft impacts the surface, and that way we can avoid that Hera actually keeps transmitting and creating noise for other spacecraft, and that's how we will turn it off.
How do you feel about something like this? I mean, like, this is your baby.
Well, let's say there's so much work at the moment to just make it fly and, make it ready on it. It's a little bit far down the road. But no, I mean, it's going to be extremely exciting. I'm so much looking forward to seeing Hera on the launch pad.
How can audiences watch this mission? How can audiences become part of that mission?
Oh, well, so there will be a series of stories that will broadcast cartoons in the coming years, so that people can follow in a nice way how Hera is going to be built and so on. And one of the projects we're discussing is also maybe to allow people to send inquiries about the Hera spacecraft, where the Hera spacecraft is, where it's going, and how it's doing. There will be a lot of images. As I said before, the data from Hera will be made available, and one of the things we really made sure is that all of the images taken from the Hera cameras will be very quickly available to the public. Maybe actually one of the things I think nobody knows yet, we're mounting a small, like a GoPro camera on the payload panel of the spacecraft. So people will actually be able to monitor and to see when the CubeSats from Hera will be released. I think it's going to be a very nice set of images, and a little bit like what Rosetta has done with Philae. You'll be able to see the various spacecraft from various angles.
Fascinating.
Yeah, it's going to be very, very interesting. I think people will really enjoy this mission. If you think about it, it's going to be probably one of the Didymos will be one of the most crowded places in the solar system. I mean, will be visited by DART, by LichaCube, by Hera, by the Juventus, and by the Milani CubeSats. So there will be five spacecraft visiting these two bodies.
After a couple of million years of solitary travel through space.
Absolutely. Yeah, exactly. So it's going to be an interesting space party.
Say, Ian, where do these guys actually come from? Where do asteroids come from in the first place?
So asteroids are what remains of the formation of the solar system. So you have to imagine that 5 billion years ago, almost 5 billion, the solar system was a nebula, a big cloud of rocks and gases, and then it started to compact, and as the sun formed, they started to spiral around the sun, and eventually to compact and create the first boulders, and then the first boulders become the first mountains, and then the first planets. So as the various planets formed, they attracted more material, and eventually some of this material got stuck, if you want, in various places, because there were the different gravity fields of the planet were moving them around, and slingshots and this type of thing. So asteroids is everything that remained from this process, and as I say, didn't make it into a planet. So they are really the primordial bricks of our solar system. That's why they're so fascinating, because studying asteroids in space is like looking at a time machine. Is looking at the material that formed our solar system. And within asteroids, you have some of the secrets of the composition of the solar system in its primordial phases.
Say, Ian, if you happen to go on a walk on the weekend and you come across a rock or a riverbed with gravel and small rocks, is it fair to say that those rocks are of the same composition as our asteroids, because they come from the same time period?
Absolutely. And we are made as the stars are made. We all come from the same place. The main difference is that asteroids haven't been weathered They didn't go through thermal cycling. They haven't gone through water. They haven't gone through tectonics. So that's why they are considered pristine material from those times. But the chemical composition, the material, the atoms is the same as we are, as the stars.
Great. Who is Ian Carnelli in this in this game?
Is a stubborn engineer, passionate about asteroids, and even above this is I'm somebody who loves the human adventure in space missions. Space missions are incredible human adventures. We are hundreds of engineers working on these two missions all across the world. We have from Japanese to Americans to Europeans, and putting all these minds together and working towards the same goal with the same passion. This is above all, I think, what is most interesting for me and what I love the most.
Does a Planetary Defense Mission director also watch space movies in his spare time?
Absolutely. I love science fiction. I love it. And to be honest, I'm always very fascinated by science fiction. There are many science fiction movies. If you look at those from the 60s and 70s, you realize today those technologies that look so crazy are available to us. And I love science fiction movies. I love how human imagination can provide solutions to problems today that actually lead us to create them, to enable those. So now I'm a big dreamer.
Nice. Do you have a book or a movie you would like to recommend watching or reading?
I loved the movie Interstellar. I love all the Star Wars, of course. And if one has to staying on the space theme and let's say close to today, The Martian, I would definitely recommend the book. Because it's
usually books are better than movies, right?
Absolutely, absolutely. So read the book. It's a very nice book, and actually, I think make people realize that Mars is not such an easy environment to live in as many dream of today, which is still something I believe one day we'll manage to do. But it's a big desert.
We shouldn't forget that we are living in paradise, I guess.
Yes,
already.
Absolutely. I mean, when you talk to astronauts, and there's always a common theme, our planet is so beautiful, and we are in here every day. We should definitely not forget it. We need to, number one thing is we need to protect it. It's the most beautiful planet we know in the universe, and we should really
maybe the only one
cherish it.
We don't know.
Yeah, maybe only one. We don't know. I personally think that there are other worlds out there, but today, so far, we cannot reach them. In any case, I mean, look how beautiful. Yeah, we need to protect our beautiful planet.
Nice. Ian, we have a fun tradition at the end of our podcast, and that is we talk about coffee. Because this is a Space Cafe podcast, and you being an Italian, you were sort of the epitome of coffee expert, I guess. So let's share an espresso that is a little bit of an inspiration, an energy for the mind, that is. And you're free to pick a topic you would like to share as an inspiration, as an espresso for the mind for our audiences. What would you like to share? Anything.
I would say multiculture, meaning that I would like people to reflect on the fact that living in a multicultural society is something that we need to learn to appreciate more. There is so much energy, there is so much potential, there is so much power into a multicultural society that most of the people don't realize. The only reason why we managed to have a space program is because right from the beginning, they were based on multiple cultures, on people coming from different countries. Look at the Apollo programs, people from Europe, people of all races, all people with different background have a different way of solving problems. It's amazing. People, we should do a movie about it one day, or a documentary. If you take a space mission and you have a moment of crisis where there's either an engineering problem nobody can solve or you don't know how to solve, you take 10 people from the program, you put them around the table, you get 10 different solutions. And the energy, the momentum, the way of thinking in a multicultural environment is so powerful, That's the only way we can solve our problems today. And so people should stop being scared, and we should stop fear-mongering multicultural societies. We need to be able to show people how powerful our multicultural societies are. The opposite side, people with different societal background, religion, and it's unbelievable. I don't know why, TVs, radios, we keep talking about problems. Let's talk about the positive side of it, and let's show how much positiveness there is into it. It's unbelievable.
Thank you so much, Ian Carnelli, for taking the time.
Thank you. It was my pleasure, Marcus. I hope I was not too boring.
Life is good when we get to deal with things like this. What do you think? Thank you for your time today. As always, check over at the mothership, SpaceWatch.Global, for additional information and treats on all the space topics you may have heard of but want to know more. I'm relatively sure something can be found over there, even for the super nerds among you. Space Watcher t-shirts look pretty cool too, by the way. Anyway, I'm glad about your increasing interest in our little podcast over here. Spread the word if you like. See you next time. I'm looking forward to it.